Started. So today and for the next few lectures, we will be talking about probabilistic models. So these are models that we train that have very explicit and sometimes very rich probabilistic semantics. Announcement. So we'll be using a lot of probabilistic manipulations in the next few lectures. So there's a probability recitation tonight for those of you who are want to do a little bit of brush up on that. And so let me just start by going back to our topic overview. So as I discussed in the very beginning, most of the useful, quote unquote, useful stuff that's in the industry right now are based on some notion of supervised learning where there is a specific prediction task that we aim to perform well at. And we can do this with linear models, nonlinear models, different choice of loss functions, thinking about overfitting, all that stuff. And including how do we actually do the learning? So what is the optimization problem? We then started talking a little bit about unsupervised learning, where the learning objective is some notion of a summary of the data or a reconstruction of the data. And some of the similar issues arise, like loss functions, model to class, optimization algorithm, stuff like that. Today we'll be looking at probabilistic modeling, primarily from the unsupervised learning perspective, although as we'll see throughout this lecture and the next few lectures, once we get into probabilistic modeling, sometimes the distinction between unsupervised and supervised learning start to become blurred a little bit. And so let's just dive right in. So today we'll be looking at an introduction to probabilistic models. In particular, after the opening part of the lecture, we'll do a detailed look at the simplest probabilistic model, naive Bayes. And we'll look at the challenges associated with it, and then we'll end this lecture with a broad overview of advanced methods. That's a typo. It's next Tuesday is hidden Markov models. I'll fix that. Okay, so probabilistic models. So probabilistic models, also known as generative models, they consider the joint distribution of x and y. As we move on to more sophisticated probabilistic models, the notion of a separate y tends to become a bit more blurry. But for now, let's say we have an x and a y, and if we were doing supervised classification or regression, the y would be the prediction target. And if we want to make a prediction on y given x, so before we would do something like logistic regression for a model of this form. Now, because we're learning p of x comma y, we have to use what's called Bayes' rule, and in order to predict p of y given x. And Bayes' rule is simply, it basically says p of y given x is equal to the joint distribution of p of x comma y divided by p of x, which equals p of x given y times p of y divided by p of x. This is Bayes' rule. It's just invoking the law of conditional probability, which is the second equality, and the third equality, actually. I should also mention that if you're simply trying to predict a y that maximizes this probability, you don't need the denominator here because you're given a specific x, so p of x isn't needed to predict the maximizer of this probability, since you can just predict the y that maximizes the numerator because the denominator is constant no matter what choice of y you have. We can do things with the joint distribution. For example, we can infer marginal distributions. What that basically means is that if we want to compute the probability of a specific y using this model, then we sum over all possible x's. This is the law of total probability. If we want to compute the probability of p of x, we can sum over all possible y's. So at this level of abstraction, the way we've written the model, it doesn't necessarily make a distinction between y and x, like which one is more important than the other, or which one should be treated differently than the others. In order for something to be a probability, each of p of x comma y must be non-negative, and over the whole input domain of x comma y, it should sum to 1. This is what it means to be a joint probability distribution. So suppose we have the following p of x comma y that we've learned. And here I've simply represented it in its tabular form. So here the model parameters of this p of x comma y for discrete x, y. So x has 3 possible values and y has 2 possible values. So the whole model can be represented by these 6 numbers. So we're going to keep it at this for now for clarity. Then if we want to compute the probability that over the data that this model is fitted on, that x equals homework, the answer is 0.5. And the way you get that is you sum over you sum over all the variables that you're not computing. So you're ignoring y, for example, then you just sum over all possible y. And if you do that with this probability table, you'll get 0.5. This is a relatively straightforward exercise. In other words, you marginalize out the y, which is the variable that you're not querying in this particular probabilistic query. Here's another example. Suppose that we know that for a given x, x equals help. Then we want to predict the probability that conditioned on observing x equals help, y equals spam. Okay. So what we do there is we basically invoke the law of conditional probability. P of y given x is equal to the joint probability p of x comma y divided by p of x. And p of x, and then p of x is equal to the sum over all possible y, p of x, y comma x. And here I reverse y and x. It doesn't really matter. I'm just abusing notation there. And so the answer is 0.6. And this is a very straightforward exercise from just reading off the entries of the probability table and manipulating it within these laws of probability. Okay, suppose we observe that y equals not, so not spam. What's the probability that for any given sample from this distribution, if y equals not, then x equals help? And again, you do the exact same thing. Here, there's no particular, at least in the way we've modeled the data, there's no particular special meaning behind x or y. They're in some sense interchangeable in their meanings. So here, if I've estimated this joint probability model, I can compute this just as easily as I can compute p of y. I can compute p of x given y just as easily as I can compute p of y given x. So the answer is 17%. And again, this is a straightforward exercise from reading off the entries of the probability table. Okay, any questions at this point? Okay, so this is nice. This model is nice. It seems to be extremely flexible in terms of the type of prediction tasks that you might assign to it. Certainly more flexible than just simply directly estimating p of y given x. So how do we train such a model? In other words, what is the objective function? The typical answer is maximum likelihood. There are a few other answers these days, although they all are basically maximum likelihood formulations. This is the direct maximum likelihood estimator, which basically says I want to estimate the probability of the data. So S is the data set. Assuming every data point is sampled independently from the true distribution, this factorizes into a probability over each individual sample. And typically we minimize the negative log likelihood, so this is the log loss over this model class of x comma y instead of y given x. And in the case of this particular model, this tabular model, it's just frequency counts. We just simply count the frequency, and so basically y equals spam, x equals help happens in 15% of the data points in the data that we sample. So the interpretation here is that given some structural assumptions about the model, so given the model class given the model class, we want to find the parameterizations of this model class that best explains the data, that maximizes the likelihood of observing the data that we sampled from the true test distribution. In this particular example, the model class is unstructured, in that we simply have a single parameter per possible unique item in our distribution. We'll look at more structured examples later on, but that's the idea. And to look at how we actually derive the answer, and this, I think this is a kind of an interesting exercise. First, let me do a reparameterization. So P of x comma y, it has to be non-negative and sum to 1. So let's assume we have these non-negative w's, and we normalize we can normalize it by just dividing by the sum over all possible x prime, y prime. So I've done nothing special here. This is simply a reparameterization of the model. Nothing has changed in terms of expressivity. But this reparameterization makes it easier to reason about this minimization problem. So I'm minimizing the log. So over the training examples, I'm minimizing the log probability, the negative log probability of P of xi, yi, which if I use this parameterization, basically boils down to this form. So if I take the log of this ratio, it becomes the log of this minus the log of this. This is the standard fact. And so the negative log of this equals minus log of the numerator plus the log of the denominator. If I compute the gradient with respect to a single parameter in my model, then basically the derivative of this guy is just 1 over w comma xy. And how many times does this gradient happen in the data set? As many times as xy, this specific xy, it appears in the data set, because this part, it only appears when xi yi equals xy. And the second part appears in every instance in the training example. For every instance in the training example, this xy appears in the sum, because the sum's over all possible xy. So the derivative of the log of something is 1 over that, and then that happens n times. So this is a very straightforward calculation. You set the gradient to 0, because the optimal solution must have gradient equal to 0. You set this gradient to 0, and you get this. So you move. So you set the gradient to 0. You move this guy to the other side of the equality, and then you divide by n on both sides, multiply by w sub xy on both sides, and you get this. So what does this say? This basically says that the solution to this parameter, to this quantity, is the frequency count. In practice, of course, people just go directly to this. For models of this form, where you know that the probability when you know that the model class is a probability lookup table, then when you're optimizing this objective, it's always the case that it's some sort of frequency count. That's the maximum likelihood solution, which should be unsurprising. Okay, of course, we may want to do some regularization. And the most common way of doing regularization for these types of function classes is to hallucinate training data. So we talked about this briefly in the first week of class, I believe, or second week of class. And so these are also known as quote-unquote pseudo counts. And so the basic idea is, we have a regularization strength. I'll call it lambda, and I have some prior probability of observing an XY pair. And then I just pretend I already observed. Basically pretend that I already observed that data. I hallucinate, I already observed that data before looking at the actual training set. In certain specific cases, you can actually derive this as a proper Bayesian prior. And I'm happy to provide references for when that might be the case. Yes?
So can you clarify where you're getting this prior collectability?
So for example, I could set it to uniform. So let's take the extreme case where I don't observe any data. N is 0. This is kind of, so just as a thought experiment. If my data set is empty, I still need to set I still want to set my model to something. What should it be? Whatever my prior is. And the most common prior is uniform. Okay, so some terminology. So probabilistic models are often interpreted as generative models, which means that because it models every variable in the data as a joint probability distribution, I could actually generate this distribution. So in other words, if I have a training set of XY pairs, I want a model that actually can generate data that looks like my training set, which is XY pairs. A discriminative model says I simply want to discriminate between the data points. So if I want to discriminate on y given x, then all I care about is does this given x fall into the positive y or the negative y, if y is a binary label. So for example, logistic regression is a discriminative model. And what I just showed you in the first few slides is a generative model. It models the total joint distribution. So what are some benefits and drawbacks? So generative models the entire joint distribution, p of x comma y, and if you want to do a specific prediction task, like what is p of y given x, you have to invoke something like Bayes' rule. One of the nice things is that because it models all of p of x comma y, it tolerates missing values. So we'll get into some details of this later on in this lecture. Discriminative models only models p of y given x. So we're actually directly modeling how to predict y given x as accurately as possible. Whereas the generative model, because it's not directly, the loss function isn't directly optimizing p of y given x, it may be less accurate if this is the only thing we care about, predicting p of y given x. And we'll see some examples of that. Another issue with discriminative models is that they cannot naturally tolerate missing data. If you're doing logistic regression, if you're doing Kaggle competition, and one of your input x's was missing, I mean, it becomes a kind of a pain to figure out what to do in that case. So discriminative models tend to make better predictions. The learning objective is literally to maximize p of y given x, or minimize the log loss of p of y given x. Whereas generative models require combining multiple estimated values, right? So if you want to predict p of y given x, it's the ratio of p of x comma y divided by p of x. And if you've ever taken any kind of numerical kind of analysis or numerical optimization course or homework, you'll know that if I misestimate the denominator, p of x, it can lead to hugely miscalibrated answers. And the training objective maximizes p of x comma y, not p of y given x. So it may be, if I maximize p of x comma y, it may be that p of x is misestimated by a pretty significant amount, in which case this ratio will be a very bad approximation to this guy, whereas if I directly just estimate this guy, I may get a much more accurate answer if that's the only thing I care about. So I mean, there's some very simple extreme cases. For example, if there's many different x's, and I have a very huge, I have a huge number of possible p of x's, and p of x to underflow a little bit. This is an extreme case, of course, but then this estimate is extremely unstable. Okay, so The benefits of generative models is that they're joint models. I can fully specify the probability distribution of p of x comma y. What does that mean? That means suppose I want to create a new data set. I want to create a new data set of xy pairs that looks like the xy pairs that I collected. How do I do that? Well, if I have a good model of the joint distribution of all the variables that of the data set that I sampled from, then I could sample from this model. So here's one idea. So suppose this is my joint probability model. Then this is a simple Python script can sample from this, right? First I sample a uniform random number between 0 and 1. I'll call that number r. I'll call that random variable r. If r is less than 0.15, I say, okay, we're gonna sample the first entry. If r is greater than 0.15 and less than 0.25, we'll sample the second entry, and so on and so forth. So it's very easy for me to use this joint model to generate a new data set that, at least under the assumption that this model is a good model, will look like the training set. Generative models can also tolerate missing values. So if we're missing a value in x, if we have many, then we can use the fact that it's a joint probability to sort of marginalize out that particular x. And we'll see some examples, concrete examples of that. Discriminative models, as I mentioned before, cannot naturally tolerate missing values. It's actually a huge headache to tolerate missing values with like a decision tree. There are many people, possibly me, possibly not, who find generative models more elegant in that to the extent that you model uncertainty using these probability distributions, these generative models tell a complete story about the data. If we have this complete story about the data, we can ask all sorts of different questions about the data. So if we can't decide a priori what's the task we want to solve, and then we first learn a generative model, then we use it to do computation afterwards. Any questions? Okay, now, I'm going to spend most of the remaining part of this lecture on a specific generative model called naive Bayes. So we're going to consider the case where we ultimately want to do classification as one of the tasks that we care about. So there's a specific y that is somehow special compared to the other attributes that we have in our data set. And if we were doing straight up classification, this y would be the prediction target. And we have a set of other attributes, x. And let's say there's capital D other attributes x and a special attribute y that in the classification task is the prediction target. And we want to model the joint distribution over all the variables. So in the simplest case, the x and y's are binary. Here's an example of x, y's being binary. And again, I'm using the probability table representation. Can anyone tell me what might go wrong with this representation as the data set becomes large? For example, I get many more than rather than d equals 2, d can be a large number. Yes.
There are some some entries that have a very small probability, so if you get many dimensions, you might just get 0.
That's right. So one of the challenges is that there are many entries, and so the numbers get smaller and smaller. There's a associated challenge with that, which is the fact that there are many entries means this model is hard to store. So in particular, this particular function class has the number of parameters that grow exponentially with d. So in fact, in particular, it's 2 to the d plus 1 in this case. And so if d equals 2, we have 8. If d equals 3, we have 16. If D equals 10, we have 2048. That's probably not a good idea. And a consequence of that is that these numbers get really small. So there are many reasons not to want to do this. And that's where naive Bayes comes in. There are many ways of dealing with this issue. Naive Bayes is the simplest one. It relies on the fact that there's amongst our attributes, there's a single attribute, we'll call it y, that's somehow special. And then there's a number of other attributes that I'll call a vector of x. And so the probability distribution of x comma y, we'll write it in this form. P of x comma y is equal to P of x given y times P of y. And each x is then assumed to be conditionally independent given y. That means that the probability of x given y factorizes as the product of each individual x of d given y. And if you work with probabilistic models, then you'll inevitably encounter what are called graphical models. So graphical models is basically what you see in this figure. And they are essentially a graphical representation of the conditional independence structure of the probabilistic model. So in particular, these arrows mean that each of these P of x's is given y. And what the arrows further indicated that if you condition on all the parents of this, node, let's say x1, then probability of x1 conditioned on all of its parents is conditionally independent to everything else in this graphical model. So people often use these graphical model representations to quickly reason about conditional independence assumptions. So this is naive Bayes. We make a quote-unquote naive assumption that each xi or xd is conditionally independent given y. So why is naive Bayes convenient? Well, it's a compact representation. So each individual quantity, in the case where x and y's are binary, is just a 2x2 lookup table. So each individual quantity is just a very small lookup table. And it's easy to estimate each of the components. They're just frequency counts. If you they're just frequency counts. It's easy to sample, and it's easy to deal with missing values. So you get all the benefits of the generative model, plus the fact that it has a compact representation that's easy to model and estimate. So, for example, this is these are the for two-dimensional x and binary x and y. This is the entire this is the entire naive Bayes model. In particular, the model complexity, so the number of parameters in this model, is linear with the length of x rather than exponential. Sorry. All right, so let's look at how we make predictions. Suppose we care about P of y given x. And the way we've structured the model suggests that y is somehow special. So this is perhaps the most common prediction task that we care about. Okay, how does that work? Well, P of y given x is equal to P of x comma y given P of divided by P of x, which is equal to P of x given y times P of y divided by P of x. This is the full Bayes rule, the first two equalities. And now I'm going to invoke the naive Bayes. So nothing here is particularly special from the first two equalities. In the third equality, I'm going to invoke the naive Bayes assumption. So P of x given y factorizes into P of x d given y for each dimension d of the x vector. And for P of y given x, I can, this is since this p of x in the denominator is fixed, it doesn't change as I vary y, then I can just simply say that this is proportional to p of y times the sum over, times overall, indexing over all d, p of x d given y. If y is binary, then I can recapture this probability by taking this quantity and dividing over this quantity over all possible y. And the reason why this form is desired is that these are the probability tables that the naive Bayes model explicitly encodes in its parameters. So if I have it in this formulation, now all I need to do is do a lookup in the probability tables that the naive Bayes model keeps track of. And that's sort of the, one second. And that's sort of the trick here is you want to use these laws of probability to manipulate things so that it boils down to something that you can directly look up in your probability tables, depending on the structure and the assumptions you made in your probability model. Yes?
How does this structure help you with missing data? It looks like you still need a reaction under y.
It's a great question. And I will answer it in about 5-ish minutes. Yeah. Okay, so let's just go through one example. This is a very simple example, but it gives you a sense of the sort of the mechanics of how these models work. So suppose that p of y equals 1 is 0.3, and p of y equals minus 1 equals 0.7. This is the p of y probability table. And then for a specific x, I'm not going to write out the whole probability table, but for a specific x, p of x given y equals 1 is 5%. So for given this y, the probability of sampling this x is 5%. And for y equals minus 1, the probability of sampling this x is 0.1%. Then if we observe y, then the probability of that, if given this x, given that we observe this x, the probability that y equals 1 is equal to about approximately 96% by doing this Bayes rule computation. So even though the probability of y equals 1 generating this x is small, only 5%, the probability of y equals minus 1 generating this x is much, much, much smaller. And that's why if we do happen to observe this particular x, the probability that y equals 1 is 96%. Okay, here's another one. So now this is a kind of interesting prediction task. I want to predict p of x1 given the other variables. Okay, logistic regression clearly cannot handle this unless I retrain the whole model and make x1 the prediction target. Well, in this case, with the naive Bayes assumption, it's simply one entry in the probability tables that we explicitly keep track of. Because because we simply keep track of this probability, if we observe y, x1 is conditionally independent of everything else. That means if we observe y, probability of x1 doesn't depend on the other x's. Okay, so here's one with missing values. So in this particular example, we're missing the y's. We want to predict p of x1 given the other x's, and we don't know what the y is. So how does that work? Well, again, we apply the law of conditional probability. This is equal to p of x divided by p of the other x from index 2 to index capital D. This p of x is equal to p of x comma y, but you sum out over the y's. So that's what the numerator is. Same with the denominator. And each of these terms factorizes. So p of x given y factorizes, like down here, and p of x 2 to the d given y also factorizes. You just don't multiply the first probability table. So now everything in this formula is something that you can look up in a lookup table that's explicitly memorized by the model, and then you run this computation, you get p of x1 given x2 to d. And the reason why the numerator is smaller than the denominator is because all of these numbers in this lookup tables are between 0 and 1, and we're multiplying by one extra thing in the numerator compared to the denominator. Therefore, the numerator is smaller. Oftentimes, when people think about these types of models, basically are basically saying, I want small pieces of these models to be in a lookup table form, so I can basically memorize that aspect of the model. Otherwise, I want to chop it up so that because otherwise, memorizing the full lookup table is exponentially large. That's basically the design philosophy of these types of models. And so what that basically means is that people often write things in matrix form. So if you want to implement these types of models fast, and you want to sort of write them out mathematically when you write out the derivation. So for example, like if this is a really complicated model with many different levels of sampling and conditional dependencies, you don't actually want to write it out in this form. The math even the notation just becomes unmanageable. You typically want to write them out in matrix form. If the notation is much cleaner, as long as you understand how to map this notation to probabilities. Excuse me. As long as you understand how to map the matrix notation to probabilities. And another reason that you want to think about it in this way is, of course, now if you actually write the code in matrix form, you could exploit the fact that existing compute architectures can do much faster with these vectorized operations than explicitly doing these for loops. Okay, so now let's talk about traditional missing values. In a traditional missing value, we're going to predict p of y given a subset of the x's and not all the x's. In other words, suppose we have two x's, x1 and x2, and we have a y that's binary, spam or not spam, and we only observe x1 but not observe x2. So we want to predict p of y equals spam given only x1. Okay, so here's how it works. By the law of total probability, this probability p of y given x1 is equal to summing over all the missing x's, p of y comma the missing x's given x1. This is the law of total probability, and now we invoke the law of conditional probability to have something that looks like this. And in this form, so everything up to here is just standard manipulations of laws of probability using laws of probability. I have not yet invoked the naive Bayes assumption. It's only after this step that I invoke the naive Bayes assumption. And I could again using the equalities that I showed you in the previous slides, rewrite the numerator and denominator in things that I can look up in the lookup tables memorized by the naive Bayes model. So that's basically something that is doable for any generative model. Of course, depending on what types of queries you think is more likely, it will lead you to restructure your model differently, because if you do too many of these manipulations, then if you misestimate any of these numbers because of errors or finite samples, these ratios and these computations can become very numerically unstable. And so depending on what type of queries you think are more likely, it'll influence the structure of your model. So the one challenge here is how do you actually compute the bottom sum? or the top sum actually, because it's only summed over a subset of the x's, not all of the x's. And here is where naive Bayes and its conditional independence assumptions can address this issue. So everything up until now is from the previous slide. And so here, this is the quantity that we want to sum over. We don't sum over all of x. If we summed over all of x, we would just get back p of y. We want to sum over all. We want to sum p of x comma y, where x1 is not a free variable and y is not a free variable, but x2 to xd are free variables. We sum over them. And I can just write this out with the naive Bayes assumption. So nothing has changed here. I just wrote it out in the naive Bayes assumption. And now I swap, and I'll go through an example of why this swap is. You can do this swap in the next slide. But I basically can swap the sum and the product. And you can do this because of the conditional independence assumption. And you get back this. So this is how you handle missing values in the naive Bayes model. If I don't observe x2, that's fine. I just use this number instead of instead of the full p of instead of multiplying by p of x2 given y. Okay. So the trick, of course, is this equality from this step to this step. And I'll just show in an example with 3 variables just to make it very explicit. It's basically inverting the distributive rule. That's all. Because everything is conditionally independent, everything multiplies in a completely factorized form, so I could just reverse distribute to, I don't even know what the right word is, but I'm just inverting the distributive rule. And that's why you can swap these two. If things were not conditionally independent, you could not do this. So if you had a different model that did not make the naive Bayes assumption, you'd have to do something else. Were there any questions so far? Okay, so the model that we learned in class so far to predict p of y given x is logistic regression. And so it's natural to, at least at a high level, think about what are the similarities and, more importantly, differences between naive Bayes and logistic regression. Naive Bayes can query from any distribution, p of y given x, p of y given only a subset of x, p of x1 given x2. It learned the full joint distribution under the naive Bayes assumption, and so you can use it to query for any distribution. Learning is very, very cheap. It just requires frequency counting. The challenge with naive Bayes, of course, is it is not optimized for classification accuracy. It is not optimized to maximize the accuracy of p of y given x. Logistic regression, you can only query p of y given x. Cannot tolerate missing values. The optimization, it's not that slow, but it's certainly not as fast as frequency counting. And you're basically minimizing the log loss of p of y given x. So here's one empirical comparison from this particular paper. And if you only care about classification accuracy of a particular p of y, so I should explain. So they did a comparison over a bunch of data sets with a bunch of different criterion, with a bunch of different approaches. This was Before neural nets became very deep, so this is from 2006, so the neural net approach weren't not as competitive as they are now, now that we've understood how to train neural nets to be much deeper. But I think the thing I want you to take away from this comparison in the context of this lecture is that naive Bayes is in the very last place. It is simply not competitive. So if your goal is to really optimize P of y given x and do that prediction very, very well, you probably should not be using naive Bayes. And this is why, this is actually the reason why we chose to put the Kaggle competition mini project where we did in this course. We want to get all the supervised learning stuff out of the way first and have you do the Kaggle mini project, and now we talk about other use cases of machine learning. Okay, so now let's talk about training. So again, we're trying to maximize the probability of observing the training data under our model. We assume the training data is collected or sampled independently from the test distribution, and so we can factorize this probability maximum likelihood condition into the product of the probabilities of each individual data point. We, as per usual, instead of maximizing the probability, we minimize the negative log of this probability because it has various more convenient mathematical properties. And now, at this point, this is at this level. Again, as I mentioned in the beginning, this is basically what we do for almost any generative model that we want to train. And so now we invoke the naive Bayes assumption on P of x comma y. So we only need to estimate P of y and P of xd given y for any individual index d. And I won't go into the whole details, but it is straightforward to derive using the same derivation techniques we saw in the beginning of lecture, that the solution is just frequency counting. So P of y equals spam is equal to the number of times we see spam in the data set divided by the number of data points. P of x1 equals 1 given y equals spam is equal to the number of times we observe y equals spam and x1 equals 1 in the data set divided by the number of times we observe y equals spam in the data set. Regularization. People typically regularize naive Bayes using pseudo counts as before. And instead of having a single big giant joint probability table, it's now a factorization to smaller probability tables, and we just add pseudo counts to each of the smaller probability tables. Typically uniform distribution. Okay, sampling. So one of the cool things about a generative model is that if you fit the generative model, you think it's a good model of the data, then in principle, you can use this model to generate samples because it is a distribution. And you can always sample from a distribution. And this distribution should look like your training set in some sense. So in other words, if I were to sample from this data set, from this distribution IID, I should get back a data set that looks like my training set. So we first sample a uniform random variable, R, and set y to spam if R is less than probability y equals spam, and set y to not otherwise. So each individual little probability table requires a new sample. And then for each xd, we sample another uniform random variable. I'll call it R again. And we set xd to according to the lookup table. So for every little probability table, we would do another sample from an independent uniform random variable. And now we have a full sampling procedure for sampling an XY pair. And the ordering basically depends on the ordering in the graphical model representation. So recall, this is the graphical model representation. It captures all the conditional independence assumptions of this generative model. And basically you need to sample from all the parent nodes first, and then condition on the parent. If you've sampled all the parents, then you could sample a child. And these children, because they don't depend on each other directly, after you sampled Y, you can sample these X's in any order. And for more complicated graphical models, as long as you obey the topological order, you can do this sampling procedure. So if this is the model, we can sample a random variable. It's 0.5, so we set Y equals spam. And then if we sample a new random variable, it's now 0.1, so we set x1 equal to 1, condition on Y equals spam. Then we sample x2, and we draw another random variable. The random number is 0.9, so we set x2 equals 0, given Y equals spam. And these two can be done in either order. Either order respects the topological ordering of the graphical model. And we could do this again. If we were to draw another sample, right? We sample 0.9 as a random number, so we set Y to not. Sample x1 given Y equals not. Sample x2 given Y equals not, and so forth. And if we assume that if we assume that these are the statistics of the data that we care about, and the naive Bayes model is actually a good model for how the data is generated, then if we trained this naive Bayes model on 1,000 data points, and we sampled 1,000 data points from this model, the sample data and the training data should look the same under the statistics that we care about. Okay, so to recap, naive Bayes is a probabilistic generative model. We make very strong independence assumptions in this model in order to get a compact representation that's easy to train. Like any generative model, we can use it to compute various probabilities. Of course, it's not the most accurate because it makes such strong assumptions about how the data is generated. Yes?
Even with those strong independence assumptions, do you know in practice if people use like hierarchical naive Bayes models, or is that common?
Hierarchical, yes, it is. I'm going to walk you. So in the remaining 15-ish minutes, I'm going to walk you through more advanced probabilistic models. Naive Bayes actually, I don't know how popular it is these days, but even back in the day, it was pretty popular. The problem is that this independence assumption sometimes is a bad one. Like if x1 and x2 are correlated, then this independence assumption is terrible, for example. You can invent your own model. So here I have two y's. I have a y1 and a y2. Y2 depends on y1. All the x's depend on both y1 and y2. If each of these arrows is a lookup table, then again I could use the same mathematical tools that we use to derive naive Bayes. We can derive this model. We can estimate the parameters of this model, just like we did in naive Bayes. Nothing really changes because how we estimate each of the building blocks is exactly the same, and we just recombine them in whatever way suits us. More generally, these models, these types of graphical models are called Bayesian networks. Naive Bayes is probably the most simplest special case of a Bayesian network. Any questions so far? Yes?
General training by Bayesian networks just requires the lookup table?
If you have discrete valued, so okay, Right, that's a good question. So about training these Bayesian networks, if your variables are discrete valued, and the number of values that each variable can take is relatively small, then yes. If your variables are real valued, then these lookup tables don't make any sense, right? They only make sense for discrete values. So if these variables are real value, people do different things. Sometimes you say, okay, well, I'm just going to bucket them. That's one thing you can do. Okay, I don't care about the actual value. I just care about where they are in the range, in which case first I pre-process the data, then I train a graphical probabilistic model. You can explicitly keep track of the fact that they're real valued, but then you have to make some other assumptions. Like, for example, it's Gaussian distributed. You have to fit a curve, right? You have to fit some kind of curve, a function to the data, because then you're explicitly modeling the fact that it's real valued. Okay, so for the remaining part of class, I'm just going to give you a survey over some other probabilistic models that have been the topic of research in the last 15 years or so. So let's start with something that's simple. It's perhaps related to the question that was just recently asked. So suppose we have the same independent structure as naive Bayes, but now each individual little probability function is not a lookup table that's discrete over discrete variables, but little Gaussians over real value, over the continuous domain. So again, y is binary, so p of y is the same. So let's just keep p of y the same. But let's say each xd is continuous, and so p of xd given y is parameterized, is a Gaussian distribution with a mean and a variance. And in this case, I'm going to keep all the variance the same, just for simplicity. And so what are the parameters of this model? Well, it's the lookup table of p of y, and it's this mu value for each dimension and each possible y. And in this case, if I want to do maximum likelihood, I don't have the slide for this, but then if you want to estimate the maximum likelihood of this guy, you will look at every data point in your data set where y equals the y that you care about. Let's say y equals spam, and then I would just fit the mean. That's how I do a maximum likelihood of a Gaussian distribution. I just literally compute the average, and I get the exact same answer back. If I were also fitting the variance or the standard deviation as a variable, then I would just compute the standard deviation for all the data points where y equals, let's say, spam. So this conditional independence structure can still be useful even if the little pieces of the probability that you're stitching together are not lookup tables. Hidden Markov models. We will be talking about this a lot in the next 2 lectures. And here we have a sequence of y's. And the probability of y2 depends on y1. The probability of x2 depends on x2. So you have this probability. This is the actual how you write out the joint distribution of an xy, where x is a sequence and y is also a sequence. And then we need to estimate, in each of these arrows is a little probability lookup table that we need to estimate. There's Gaussian mixture models. This is a probabilistic version of k nearest neighbors. Excuse me. This is a probabilistic interpretation of k-means clustering. So each data point is associated with a membership to a Gaussian distribution. So we have a z, and if there are 3 quote unquote Gaussians that generate, if there are 3, so this is just a one-dimensional example. If there are 3 Gaussians that generated this distribution, we want to learn that there are three Gaussians. If you were to draw this out spatially in 2D, this would look like 3 clusters. So this is actually just a probabilistic version or generative model version of k-means clustering. So how you would sample data here is first you would sample a cluster. So each cluster has a base probability of being sampled. So, and then you would sample from one of the clusters, and then you would sample a data point conditioned on that cluster, and that data point will be a Gaussian distributed. Topic model. So these are typically these are originally developed for modeling text. And the idea of a topic model, in this particular case, it's called latent Dirichlet allocation. A latent Dirichlet allocation posits that documents can be represented as a mixture of topics. So if we had k topics, then what we do is when we sample a document, we first sample a topic mixture distribution, that's theta. And then we sample a number of words. Each word we sample from the topic mixture. So there's k topics. Each word is sampled from a topic, and then the word is sampled. The word that we actually sample is conditioned on the topic that we sample. So this starts to get very complicated. Fitting this model can be very complicated. After the model is fitted, after we've estimated each of these arrows, then sampling is fairly straightforward. So here's some examples of LDA. This was the top result from Google search LDA example when I created this slide last year or 2 years ago. So there was no bias that went into selecting this as the example, but you can fit an LDA model to all of Sarah Palin's emails. I guess everyone knows who Sarah Palin is, but time flies. And these are some of the topics that was uncovered. Okay, moving on. One more slide on this example. So if we were to actually look at a document, then each word, then if we assume that a document is a mixture of topics, then one particular document could be a mixture of two topics, and each word is associated with a topic. So if there's a red topic and a green topic, and this document is a mixture of those two, that's what the theta represents. And each word then is sampled to have exactly one of those two topics, and then you sample the word from that topic that you sampled. So Z indicates the color. So we sample a topic from the topic distribution, which is theta, and then given the color, we sample the word. Yes?
How are the topics chosen?
So there are k topics, and the k is chosen a priori in this case, and they're chosen by maximizing likelihood.
Oh, or the names are just given out?
Yes, the names of the topics are given by inspecting what words appear frequently for this topic. Yes. Okay, so of course these days, people have been looking at ways of combining generative models with deep learning, because deep learning has been so successful and easy to use these days. And so here's just one example. This isn't really a generative model in the strict sense of what we've covered in class so far, although I'll give some examples where it is. In this example, you condition on an input, and then you want to predict an output that has a style according to another image. So here's the input image. If we condition on this style, we get that as the output. So these are things you can do with deep networks. One area that has become very popular is deep adversarial, generative adversarial networks, where the training set is basically the training set of typically images, and we want to build a probability distribution using deep neural nets over this set of images, so that if we sampled from it, we would get back a set of images that looked like the images in our data set. So I showed you this example from the previous lecture, where the training set is a distribution over images, in this case a celebrity image data set. And we learned in the previous lecture, I interpreted the Z as an embedding. I'm going to make a different interpretation in this lecture. Both interpretations are valid, but I'm going to make a different interpretation, which is that I have a prior probability. So if I were to draw this as a graphical model, first I sample the Z's, and then I have a mapping from the Z's from Z space to image space, and that mapping is a neural net. So if I were to, so rather than this thing being a lookup table, this red box being a lookup table, it is a neural net. And so this is a deep generative model, and this is what I mean. Now how do I sample? Well, Z is typically Gaussian distributed. So I sample Z as a Gaussian random variable, and then this neural net maps from this Z to an image. And now, in order to sample new images that, in this case, hopefully look like the images in our training set, we just first sample Z, and then we run this neural net through this Z, and we get this image. And again, we'll discuss these things further in the deep generative models lecture. WaveNet. So if you have a Google device like an Android, if you talk to it, it talks back to you, and that audio is generated by a deep neural net called WaveNet. So again, it's a probabilistic model. It combines, you can sample acoustics, statistics from it. Of course, condition on a piece of text you want to say, of course, but that's how it works. Some work coming out of my lab. We've been looking at modeling distributions of non-deterministic behavior, such as offensive behavior in let's say, basketball games. So this is something that we sampled. We can, from the same initial condition, so you observe the initial burn-in period, and then we want to sample distributions of likely outcomes. So we're collaborating with various sports analytics companies to think about how these types of techniques can be used for analysis of replays, for example. And so if you were just only sampling this player in green from this initial burn-in, if you draw multiple samples, if you drew multiple samples, you get multiple outcomes. You get different outcomes. So if you sample multiple times, you get distribution outcomes that hopefully reflect the distribution of things that you observe in the replays from, in this case, it's from the NBA, where if you had an initial condition, if you observe something like this happening, what are the possible outcomes of having observed this happening, and hopefully these outcomes match the actual distribution you see in the data set. Okay, so just to recap, generative probabilistic models have many properties due to the fact that they try to model the entire joint distribution of the data. They can quantify uncertainty. They can tolerate missing values by doing marginalization. They're connected to unsupervised learning in that they're trying to come up with a summary of the data. They are not trained to optimize for prediction accuracy. So if you have a very specific targeted prediction task of a specific variable, let's call that variable y, then these methods are not going to have to be the most accurate for that specific prediction task, which was what we spent the first half of the course on. These days, they are used to generate new samples. So deep fake is the buzzword for these types of applications. And the basic idea is that if these probabilistic models are have, rather than probability lookup tables, which are fairly simplistic, the probability little modules are now deep neural nets, then we can generate things that look actually very realistic. We can capture many statistics of the data distribution so that we can generate things that look real. This has been particularly successful with images. And this spring, I'm teaching CS159, Advanced Topics in Machine Learning. And the topic of this spring is deep generative models. It's a 9-unit class. We read current research papers, and you do a research project at the end of class. No homeworks, no final exam. But the research project is non-trivial. Okay, so the next 2 lectures, we'll look at hidden Markov models in depth, which is going to be the bulk of homework 6. That's it.